Okay, so now we're into integration scenarios for Chapter 10. And we're looking at figure 1025. The title here is European Climate Foundation Roadmap 2050. Showing how renewables could supply 80% of Europe's electricity by 2050. Okay, so Europe, so the world is at 16 terawatts. Europe is at 16 terawatts, and I guess we did the terawatt hours last time. I don't remember what that is off the top of my head, but in terms of energy though, Europe is at 3,000 terawatt hours per year. And what they are looking to do would be to get to 5,000 terawatt hours per year by 2050. In general, it's a higher quality of life. I don't know where all that energy is going. Maybe longer showers, massage chairs, missions to Mars. You know, that takes energy. Yeah, flying your drones around. But these different scenarios are yes. So renewable energy scenarios. So nuclear existing, let's just look at what's there. This big pink would be phased out more or less by 2050. Fossil fuel existing, it's over half the profile. And they're looking to just phase it all the way out. Now I think another thing to mention is that this is going to happen either by default or by design. If we go back to the worldometers, let's look at energy. Um, 1.3 trillion barrels left, 40 years to the end of oil. This one always freaks me out because you hear about gas being like, oh, we got a frack, we got a frack, we got a frack. 59,000 days left? I guess they don't put the number of years on there. I guess in this scenario, it's actually a little bit longer than oil. Yeah. Barrels of oil equivalent. Yeah, this is a slightly different format that I've seen before. Barrels of oil equivalent. So they've got coal in terms of barrels of oil equivalent. There's a lot of it, and well, as I said before, let's just leave it in the ground for future generations.
It's 151,000. It's not very many days.
No, well, how many days is that? I guess if we add those guys up, let's just do it. What the heck? 150,000 plus 60,000 plus 14,000 equals, divided by 365 equals, well, yeah, 600, yeah, that's, so 600 years worth of fossil fuel left. It's just business as usual, but it looks like that if we burn it, we're going to have some major problems. That's longer than I thought.
Still not that long.
Still not that long.
About 6 generations.
What's that? Well, let's divide that by 20. 25 maybe. 25 generations.
Don't make it look so.
Yeah.
Put it in the bank.
So, but if we move towards renewables, then and we know there's plenty there. The resources there. It's just a matter of the political and financial will to make it happen. Okay, so we're looking at Denmark in the top left, 1960 to 2010. They've come on pretty hard. You can see wind, and you can see other renewables. A little bit of well, not as much wind as I would have thought there for Denmark. I can't really. Can you see that? Oh, there it is. Oh, other renewables. Yeah, I thought Denmark was more. I see the wind coming on, this little strip of blue right here. I thought it was a little bit bigger, but they've also sort of joined the fracking revolution. Unfortunately, 1980, and then figure B is Denmark's 1983 alternative energy scenario. And the Danish government's 81 business as usual projection. So this would have been the projection. Total energy supply, petajoules per year. Yeah, I don't know how they intend to remain, have a high quality of life with this much of a reduction in total energy, though. I don't know if they just stop driving or what.
Can you run their cell phones?
Yeah.
So that happened for you.
Okay, so here's your next figure for what renewable energy might look like. So you've got heat pumps, PV modules, offshore wind, offshore wave, this large grid that we mentioned. Industry uses it, homes use it. You've got a power plant that's running off geothermal. Heat pumps are doing this seasonal heat storage like we just talked about. Electric cars and a little bit of biomass. So this is global, and I see this, and I'm a little bit confused by it because, as we know, our primary energy consumption. I don't know if they just didn't update this figure or what, but our primary energy consumption is actually 500 exajoules per year. So this is a little bit confusing to me. You can see that oil is still in the mix, coal is still in the mix, natural gas is still in the mix, but by 2040, they're no longer being used. But all these more diverse renewables are. So there's algae, there's crops, crop waste, traditional biofuel, waste, there's hydro, geothermal comes on big, a little bit of geothermal electricity, solar thermal, concentrated solar for heat, concentrated solar for electricity, and then wave, wind. So really everything we've been talking about so far in 102 is going to be part of the future profile. And here's electricity historically on the left, and then projections on the right. So you've got the IEA, International Energy Agency, on the blue so-called blue map, and then what the Greenpeace folks think might be a better scenario for planet Earth, keeping it under 500 exajoules, and very little oil, very little gas, almost no coal whatsoever, no nuclear, but a bunch of solar and geothermal. Global electricity generation. And I think these guys were pretty accurate, showing sort of a peak in 2010. That's pretty similar to what Shramsky showed as well. Again, different scenarios just for electricity generation. Greenpeace kind of taking the hardest stance on solar, geothermal, a lot of wind, and everyone's about the same on hydro. That's not going to change a whole lot. Okay, I think that's about it for the chapter. Let's see if there's anything else in here. I'm going to read one little paragraph from page 518. I did not know that Greenpeace itself had its own energy scenario, but it says right here, Greenpeace acknowledges that implementing its advanced revolution scenario would entail a high initial capital cost, $18 trillion in the next 20 years or so. But because of its much lower fuel cost, so you don't have to buy the fuels, it would have a lower overall lifetime cost. So you pay it now, but you don't have to pay it later. It's also worth noting that these costs do not take into account the very large external social and environmental costs of fossil and nuclear fuels. So we don't have to store nuclear fuels underground, and we don't have to store carbon dioxide in the air. Moreover, conventional economic analysis, as explained in Appendix B, uses discounting techniques that have been the effect of minimizing the impact on future costs, so are biased against high capital. Low fuel alternatives like renewables. Greenpeace also calculates that an extra 8 million green jobs would be created globally in this scenario. You gotta love that. Okay. So, section 1011, summary conclusions. Says this chapter has reviewed the conditions under which the various renewable energy sources can continue to make increasingly significant contributions to the world. Began by reviewing the existing systems for distributing energy, then looked at the potential contributions to reduce global emissions. We looked at the magnitude that renewables might make in the UK, as well as in Europe. And then we looked at several other scenarios. Okay, and then finally there's the second to last paragraph I like here too. It says, however, it seems difficult to avoid the overall conclusion that renewables are likely to play a greatly increased role in future energy supplies. As we've seen, the relatively conservative IEA, International Energy Agency, suggests that renewables by 2050 could be supplying some 40% and of primary energy, 50 to 75 for electricity. And if history should prove the even more optimistic world, I got to hear from the World Wildlife Federation president a couple of years ago, and he's way on board with this. And Greenpeace projections to be more accurate, renewables could be supplying up to 90% or more by mid-century. And I really hope we get the political will to do that, because a lot of times it is tied up in financial decisions, and it seems like a lot of the wealthier financiers are looking forward to funding renewable energy projects. Yeah.
The little guys are learning that if they just finance it themselves a little faster, like the hydrofusion that is privately financed. And they're saying that's kind of why this one's more advanced and has a higher chance of working. Not because it was privately financed, but because it was privately financed, they were able to get the research, the technologies, the experiments, and everything.
Yeah, I think you're right about that. A lot of times the private sector puts a lot more pressure on advanced than the public one. You might have money going into educational outfit, and there are some bottom lines, but typically, the bottom line is a little more nebulous than a capitalistic company. So capitalistic model, I should say. And I think we did the math. Was it in this class or was it on the financing dollars per kilowatt for a solar thermal system? Did we do that last time, or was that in 101? I want to check my notes because it was pretty fun.
I think we might.
Let me pull it up in Excel. I just want to review that one more time because it came out remarkably. It didn't come out as great as I wanted it to, or I expected it would, but it was still quite competitive. Let me just see what that is. Chapter 10 integration. Yeah, we did it right here. It was a good one. I love that one. So here's your 500 exajoules per year. That's joules per year. Megajoules per year. We converted that to kilowatt hours. Yep, did that correctly. Converted that to megawatt hours per year. Gigawatt hours, terawatt hours, petawatt hours. Oh, that was the number I was looking for. So the humanity consumes 139 petawatt hours per year. Let's see. Exajoules, I think they had, we were looking at some figure here. Terawatt hours. So this is 3 petawatt hours. Again, that doesn't seem like enough. Oh, that's again because this is total energy and this is just electricity. So, okay, so that's our global consumption. Yeah, so what we're looking at is the economics of building a solar thermal technology. And we decided if we put $300 of materials, $800 of labor, I'm sure we could bring that down if we got an assembly line going. A couple $100 of installation, you've got a $1,300 solar thermal heat exchanger. It's going to make 2,000 watts at its peak. Its capacity is, again, this was just Missoula numbers, so 4.4 divided by 24, 18% capacity. It's going to make on average 367 watts. Converted that to kilowatts. And then we just went ahead and said for $1,300, 367 watts, you're looking at $3.55 a watt. Not too bad. It's well under $5. It's solar cells themselves are down around 60 cents, and most installs are $5 to $10. This is very competitive. So it might last 10 years before you have to replace it. That's 87,600 hours. Over its lifetime, let's see where that came from. Over its lifetime, it's going to make this many kilowatt hours, so 0.367 kilowatts times 87,000 hours comes out to be 32,000 kilowatt hours. You might do some operations and maintenance. It's going to cost you $2,000. The levelized cost, so I added the install and the annual and divided that by the total kilowatt hours, and it comes in at a dime.
Wow.
Yeah, I love that math. So let's start making them, Shauna.
Let's do it.
Let's put it in the building code. Bring it to Zootown big time.
California can do it. Why can't we?
Yeah.
Oh, California doesn't have more.
It's got more what?
More sun.
More sun, yeah. Yeah, if we were somewhere else. But on the other hand, but California doesn't mean well, I think everybody needs hot water, but in general, if you're in California, you're not really running the heating system that much. I mean, maybe if you're San
The older
Francisco,
folks,
yeah, old folks, yeah. Okay. All right, well, that's all I got. I know we're only at 20 minutes, but anything else to knock around? Yeah. I feel good about this chapter, and I hope everyone who's, taken this class and, made it through all the lectures can really look forward to a cleaner, greener future. I think we have to.
Would be nice.
Yeah.
Not having to hear about, don't ruin your stove.
Yeah.
I heard that on the radio and I said, what do these people do?
What were we talking about?
Because I guess it's the first I've ever heard of it being in Missoula.
Oh.
You have smog days and
Oh.
not allowed to light your stove.
Oh, yeah.
What do people do when they can't light their stove?
Yeah, I proposed this in my talk, but I think we should have residential carbon sequestration, or at least neighborhood scale, where the gases are being piped through the sewer system, and the sewer system's already there. Put a little cap on each cover, and then utilize those gases locally rather than just letting them head off in the atmosphere.
Letting the water
Yeah.
heat later.
Yeah, because it'd be great to use all this great biomass around here for heat.
I keep telling them when I was living in Butte, that East Ridge catches on fire, this whole Butte is gone.
Really?
Because that East Ridge is probably 3/4 beetle kill.